In this video, I'm going to show the image of why you need the adaptation in a discrete-time equalizer and how to do it. As we discussed in the series over equalization videos, the goal of a link or a data transmission is to achieve a bit error rate under a certain level, like ye-12 or ye-15, and so on. In other words, we hope the receiver sampler can make the right decision most of the time. Do you have any circuit image of how we help the sampler or this flip-flop to make the right decision? Think about the time domain images for 5 seconds. Right. You may want to sample at the peak voltage or the middle of the eye here. But how? Any further circuit images? In the Y timing video, we show the clock data recovery will perform the fast tracking at the data transition point and then sample in the middle of the 2 consecutive transitions. Which is the maximum voltage here? How about the voltage domain image? For example, do you think which eye can achieve a lower bit error rate? IVLA or IVLB? That's right, VLB. Increasing the VL or input swing of the sampler will help us reduce the bit error rate. But here we assume the sampling time TS will be in the middle of the eye here, and in the following slides for the discrete time system. So we must remove the ISI from the band limit channel by applying either the FFE or DFE discrete time equalizer. Assume we've known the required swing target, which is the green level D-left here. As you can see on the left hand side, with the DFE coefficient value set to all zeros, the I high is less than the minimum required swing, SW mean. Therefore, the error might occur during 1 million or 1 billion bits. To reduce the bit error rate, we may want the target level or swing to be larger than the minimum required swing with a certain margin. On the right hand side, if the DFE's tap coefficient value is set to 9, 6, 4, 3, 2 from tab 1 to tab 5, the DFE will increase the I high to be larger than the minimum required swing, or even to the target level D-left. Then the SerDes link will be able to achieve a bit error rate less than ye-12. And again, that's the reason for applying the equalization. But the question is how to set a coefficient. Is it easy? Could you please think about the changes of the circuit images here before producing any solutions for 5 seconds? Bingo! This is your system image of a discrete-time equalizer, TX-FFE and RX-DFE. Then, there are lots of unknown factors here. For example, do we know the TX output swing? Do we know the channel loss? Do we know the CTOE gain at the receiver front end? Under these unknown conditions, how do we adjust the FFE's tap coefficient C0 to Ci or the DFE tap coefficient H1 to H5 such that those 2 discrete-time equalizers can open the eye to the required data level D-left? Think about your circuit images for 5 seconds. Bingo again! The simple image could just build a feedback correction loop. For example, the goal is to get the sample yi to be the required data level D-left. Is something wrong here? Think about your circuit images for 5 seconds. Correct. Equality might not always hold here. First, let's take the precursor as an example from the channel's pulse response. Please be advised that the precursor can be reduced by FFE, CTOE, but there's no way to remove the precursor completely. So the residual precursor will break the equation, and the DFV cannot remove the residual precursor RSI with the HI tab coefficients. In addition, there are some residual precursor here as well. Due to the final tabs, quantization error, the feedback timing constraint, etc. of the DFV, that's not feasible to always get the exactly target level. Again, if we cannot make the sample data swing level to be exactly what we want, what could we do? Any other images in your head? Well, if not equal, we just need to accept the approximate target swing by minimizing the error or difference between the sample data and the required data level. Let's take the discrete-time nth order FIR filter as an example. The left-hand side is the input x of n after the channel but before the FIR. The right-hand side is the output signal y of n after channel and the FIR. The Ci is ith tab coefficient of the filter and would be the weighting of the ith delay of the x over n. Then the output y of n is the linear combination of the Ci times x of n minus I with I from 0 to n. For the error between the y of n and d left, we don't care if the error is positive or negative. Therefore, we can take the approximation goal with the least mean square LMS algorithm. As you may know, the LMS concept is not new and has been applied in the linear systems of several engineering areas for decades. Let's take a close look at the LMS with a few examples here. Assume the input is coming from the FIR filter, which consists of a linear combination of several tabs. Please be advised that FIR is the main exercise. We don't care or really focus on how the I shape is equalized here. The plot here shows one of the FIR equation application. The concept of the LMS is straightforward, but we need an application algorithm to find the local minima of a differentiable cost function. The most popular one is the gradient descent algorithm, and that's the one we will go through in this video. To get started, we must take major sample y of n, subtract the target d left to get the error and then the square error. What can we do to reduce the error? Think about your own math images for 5 seconds. Bingo! There's a parabola here. So you can take the derivative of it. Then derivative should follow the gradient to the derivative equals to 0, which is the place of the minima error you like to go. Then the derivative of the square error in the linear regression would be the gradient descent. For a particular Ci, the derivative shows the correlation would be the Ci input x of n minus I and the error, which is the output y of n minus the d left. But do you see any pitfalls of the circuit images here? Think about it for 5 seconds. Yes, one important assumption is that the ith delay of the x of n is uncorrelated to other delays, which means the data stream in each sample must be uncorrelated in the time domain. In other words, the data spectrum must be y in the frequency domain. If the uncorrelated data is the constraint, would that be true in your study system? Usually, it's applicable to some protocol like the Ethernet with scrambling. Therefore, you must understand your study system well before applying the LMS adaptation properly. Once we understand the LMS fundamentals, then we can easily figure out how this coefficient will update it. Again, the coefficient update should follow the gradient. So after we got the gradient, we can point the coefficient where to go during every trial. For example, Looking at the coefficient Ci, the coefficient Ci at the next time n plus 1 will be determined by the coefficient Ci at the current time n, subtract the gradient, which comes from the product of error and the corresponding input to the coefficient. Please note that the constant b is just a normalized number. Let's have the sanity check image of the updated coefficient one more time. In the magnitude, if the magnitude of the error is small and input is small, then the gradient should be small, and vice versa, which means you are close to the minimum place. How about the sign of polarity in the equation? If the sign of both error and input are the same, which means the swing of the f contribution is too big. Therefore, the coefficient should be decreased to reduce the swing and vice versa. Lastly, how does the coefficient update direction in time? The coefficient update from the parabola plot will be move the coefficient in the direction to the gradient to the slope of equals to 0. Another simple image for this is to put a ball at the edge of a ball, and then the ball will just drop to the bottom of the ball. To help you understand the LMS adaptation further, let's apply a simple case study of the VGS gain adaptation, which is one-tap FR filter. Assume the target swing at the sample's input y of n is d left, and we apply the least mean square here. If you minimize the mean square error to get the gradient of the adaptation, for example, the gain of the VGA or the C0 start at the initial default value with the maximum error, then the C0 value was increased at the next sample C0 of 1, C0 of 2, then jump back to C0 of 3 through a negative feedback and settle down to the final gain value C0 of 4, which makes the swing close to the target and the gradient or slope be 0. Lastly, look at the swing adaptation from the eye diagram one more time. Initially, at time 0, the eye opening is small since the VGS initial gain was not big enough, and then the big error or big gradient drive the VGS gain a much higher value to increase the eye opening quite a bit. At the time 1, at this moment, the magnitude of error gradient is not big, but the sign of error is still negative. Therefore, the gain at the n equals 2 will increase the eye opening slightly with a little bit overshoot at time 2. At this time, the magnitude of error is small, but the sign of the error is positive, so the gain at the time 3 will be updated to drive the eye opening smaller with a little error. Finally, the eye opening will converge to the target level d left at time 4. Here is a summarized image you may have for the adaptation in a discrete-time equalizer. Let's start with a style open eye VLA, which cannot meet a target bit array without a discrete-time equalizer's help. For the initial eye opening VLA shown here, the equalizer was disabled by setting all the tap coefficient to be 0. If all the tap coefficient was set to the wrong value with a maximum error, the eye opening VLC would be closed. So, a proper least mean square LMS algorithm should be applied here to help the coefficient follow the gradient to the optimized value to open the eye as the VLB shown here, which makes the error difference of the eye swing and the target level has been minimized. Lastly, the required gradient image and the equation are shown here. Through the LMS, the VLA will start with a certain error swing and M0 gradient, then move to the VLB with a 0 gradient without moving the wrong direction to the I VLC here. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share a video link with people who may be benefiting from it.